A warm welcome to the second film in our single-skin facades series, in which we explain what thermal bridges are and how to address them. The weather here in Germany is so cold for several months of the year that we need to heat the interior of our buildings. You can see how much it costs to heat your flat, for example, by looking at the service charges you pay with your rent. On average in Germany, heating costs, excluding hot water, represent 57% of these service charges. The average cost per square metre is €1.24, that is €42 a month, or €500 a year for my son's student accommodation. The money is literally escaping through the building shell. Transmission is the term used to describe the process by which heat passes through part of a building. It is a flow of energy caused by a difference in the temperature on either side of the building. Professor Grunewald, our colleague in the Building Physics Department, has produced this isotherm graph for a 49 cm thick wall made of vertically perforated blocks. Isotherms are lines that link points having the same temperature. It shows how the wall gets progressively colder as we move from the inside to the outside. That is why the interior has to be heated. Here we can see how an exterior wall made of sand lime bricks that is just 24 cm thick behaves at the same temperatures. The interior temperature is much lower than with the 49 cm thick vertically perforated block wall. More heating is required because the wall has a lower thermal insulation characteristic. We use the thermal transmittance coefficient, or U value, of the component to describe this characteristic. Just like the difference between a thick and a thin winter coat, the U value depends on the thickness of the layer of material. 24 cm is only half as thick as a 49 cm thick wall. The U value also depends on the heat conductivity of the building material used. Here you can see a vertically perforated block and a sand lime brick with the same dimensions. The vertically perforated block has a lower and therefore a better U value than the sand lime brick because it is a poorer conductor of heat. This correlates with the bulk density of the block, which is specified in mass per unit volume. The lower the bulk density, the lower the conductivity. However, high bulk density also has certain disadvantages in terms of soundproofing and compressive strength. Imagine a building constructed with 49 cm thick walls of vertically perforated blocks to ensure that the building shell provides a good level of heat insulation. Even this well-designed construction will have some weak points in the form of thermal bridges or areas of discontinuity where greater heat penetration occurs. This photograph, taken using a thermal imaging camera, shows thermal transmittance in a monolithic facade. The red patches show areas where more heat passes through the fabric of the building to the outside, the blue patches those where heat penetration is lower. There are three types of thermal bridge. First is the geometric thermal bridge. This occurs where the exterior surface of an element is smaller than the interior surface due to the shape of the heat-conducting envelope. It's best illustrated using the example of the corner of a building and the corresponding isotherm graph produced once again by Professor Grunewald. A structural thermal bridge exists when weak points are created in the building shell due to the type of joints used. Here you can see what happens when a reinforced concrete slab is laid on a vertically perforated block wall. The reinforced concrete has a higher bulk density and thus greater heat conductivity than the blocks, and the thickness of the block wall is halved at the point where the slab is supported in it. As a result, heat transmittance at this point is significantly greater. Material thermal bridges occur predominantly where the fabric of a building consists of more than one material. Here, Professor Grunewald has produced an isotherm graph showing a rafter roof. From it, we can see that heat transmittance is greater at the timber rafters than in areas where insulation is present. This is because wood is a better conductor of heat. Geometric, structural, and material thermal bridges are unavoidable, and every building will have some weak points of this kind. When working with building physics and structural engineers, however, the architect's attention should focus on minimizing thermal bridges and compensating for unavoidable weak points. For example, a special purpose component with better thermal insulation properties can be fitted at the point where a floor slab ties into a wall. Summary. Transmission is the term used to describe the process by which heat passes through part of a building. We use the thermal transmittance coefficient, or U value, to describe the thermal insulation characteristic of an element. The U value depends on the thickness of the element and the heat conductivity of the material of which it's made. Even this well-designed construction will have some weak points in the form of thermal bridges or areas of discontinuity where greater heat penetration occurs. There are three types of heat bridge: geometric, structural, and material. Please look at the third film in our single-skin facade series, in which we discuss how to prevent the ingress of water into the fabric of a building.